Let's start with an experiment of tossing a coin. Okay, so if we toss the coin once, there are two possible outcomes we can get. We can get either a head or a tail. If we toss the coin twice, then what are the possible outcomes we can get? We can get either a head-head, a head-tail, tail-head, or a tail-tail. Now, a set of all possible outcomes of a random experiment is actually called a sample space, and it's donated by capital Omega, right? Now, this is a sample space by tossing the coin once, and this is the sample space by tossing the coin twice, and we can also likewise define another sample space by tossing the coin 3 times, and the possible outcomes would be head, 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 tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, tail, tail, tail. Okay. Now what I would like to do is I would like to define 2 random variables. Let's say I would like to count the number of heads, and that random variable I'm going to denote by x, and let's do another one, y, where I'm going to count the number of tails, right? So if this is how we define x, the value of x here would be, in this particular experiment, here, if this is the outcome, the value of x would be 3 because there are 3 heads and we are counting the number of heads. Here the value would be 2 because there are 2 heads, again 2. Here there would be 1, 2, 1, 1, and 0, right? So we're just counting the number of heads because that's how we define a random variable to be. Likewise, let's count the number of tails. Here value would be 0 because there are no tails here. There's 1 tail, 2, 1, 2, 2, and 3, right? So very simple. We're just basically counting the number of heads here and number of tails. Now this is a random variable because obviously the value depends on the outcome of our 3 coin tosses, right? So if the first 3 coin tosses were tail, head, head, the value of x would be 2 and y would be 1. So now we can define what a random variable is. Random variable is a real valued function that assigns a outcome of our sample space and gives it a real value, right? So basically we can denote, let's denote an outcome of our experiment as omega, okay? So what we're saying is x, which is a random variable, takes on a value of omega and basically gives it a real value, right? Likewise, y is another random variable defined on the same sample space. So it's basically taking another, it can take various outcomes and basically it will assign a real value as well. Even though the experiment is exactly the same, which is tossing the coin 3 times, but we basically have defined 2 separate random variables, and depending on the coin tosses, they assign these coin tosses different values, right? So in our example here, x basically of h, so the outcome is h, this function, which is a random variable, basically would assign it a value of 3, whereas y would take the same particular outcome but would assign it a different value of 0, right? So these are basically you can think of them as real valued functions that operate on our sample space and assign different values, right? Great. Now let's take this example a little further and let's say that, let's make it a little bit more domain specific. So let's say that we're conducting the same experiment. What we're going to do is we're going to take a coin, we're going to toss it twice. So what is our sample space? We can get a head, tail, tail, head, or a tail, tail, right? Now let's say that there is a stock that whenever the value of the coin toss is a head, stock goes up by a factor, and if the value of the coin toss is a tail, it goes down by a different factor. Okay, so what we're saying is we're basically starting with the stock whose value at time 0 is S0. We're going to toss the coin, and if the value is a head, the stock goes up. If the value is a tail, the stock goes down. Likewise, we can toss the coin again, and we could say it's a head, 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 tail. So again, if it's a head, stock goes up. If it's a tail, stock goes down. And likewise, S2, first was tail and second was head, tail, tail. So these are the 4 possible outcomes of our experiment. And we've defined, we've said that okay, there is a stock that if the first coin toss is a head, it basically takes on this value. If it's a tail, it takes on this value. And likewise, if we toss a coin twice, the stock can take any one of these 4 possible values, right? Now, let's think about this example. Now, if you look at, the value of the stock at time 1, denoted by S1, it basically is a random variable because, obviously the value of S1 depends on if the coin toss is a head or a tail, right? And if the first coin toss is a head, value would be S1H. If it's a tail, it would be S1T. And it's random because we don't really know how the first coin toss is going to turn out at time 0. Okay, so S1 is random. Likewise, S2 is also random because it depends on the first 2 coin tosses, and we really don't know how the coin tosses are going to turn out at time 0. Okay, so S2, which is the value of the stock at time 2, is also random. Well, S0 is a special case because the value of S0 is known at time 0, and it doesn't really depend on the first 2 coin tosses. So these kind of random variables, we call them degenerate random variables. Okay, so what we've done is we basically have defined 3 different random variables here. This S1 depends on the first coin toss, S2 depends on the first 2 coin tosses. S0 basically is a degenerate random variable. It doesn't really depend on any coin tosses, and it's not really random, okay, because the value is known at time 0. Likewise, we could just continue this experiment. We could toss another coin and we could basically define a value of the stock at time 3 as S3, and that would be random variable as well. And likewise, we can continue the experiment to n number of, we could say, okay, we toss the coin n number of times and the value of the stock at time n would be Sn, and depends, this would be random because again it depends on the first n coin tosses, right? So that's pretty much what I wanted to talk about for random variables. One thing to actually observe here is when we were conducting our first experiment, and when we were counting the number of heads or a tail, we could define the random variable without really worrying about what is the probability of a head or a tail. So nowhere in our discussion of random variable we've actually talked about probabilities of various outcomes, right? Because they didn't really matter. We just were concerned about, we defined a random variable counting heads, and depending on what a sample space was, we could actually define the value of the random variable as well. Okay, so probabilities didn't really matter for defining random variables. And likewise here, we defined a hypothetical stock process, and basically depending on if the coin toss was a head or a tail, the stock went up or came down. And we didn't really, just to define what these random variables were, we didn't really worry about what are the probability of various outcomes, right? Now, probabilities are going to start mattering when we want to talk about distribution of random variables, which is a topic we're going to take on maybe in the next class, or sometime later on. And that's the only time when we basically going to combine the random variables with their probabilities, and combining the two will give us distribution of the random variable. But it's a topic which we're going to discuss in maybe in the next class or so. Okay, so that's pretty much all I wanted to talk about today. Just remember that random variable is a function that operates on a sample space and assigns it a real number. And for defining random variable, we really don't care about defining probabilities of those outcomes, okay? And those two concepts are pretty important to remember. Okay guys, so see you in the next class. Hi guys. So in the last lecture we talked about random variables. Today we're going to start talking about probabilities. So let's start with exactly the same experiment that we conducted last time, that we're going to take a coin and we're going to toss it 3 times. Let's write down all the possible outcomes of the experiment right here. So if we toss a coin 3 times, we could either get a head, head, head. We could get a head, head and a tail. We could get a head, tail, head. We could get a head, tail, tail. We could get a tail, head, head. We could get a tail, head, tail. We could get a tail, tail, head. Or we could get a tail, tail, tail. So we've conducted an experiment, and these are all the possible outcomes of that experiment. So this is basically called a sample space and denoted by capital Omega. Let's further take the experiment and define the probability of a head as P and probability of getting a tail as Q. Now in our experiment of tossing a coin, we can either get a head or a tail. These are the only 2 possible outcomes. So we're further going to define probability of getting a head plus probability of getting a tail as 1. Okay. Now what we need to do is, I would like to actually define what is the probability of all of these outcomes. So in particular, let's start by defining the probability of getting a head on all the 3 coin tosses. Now before we do that, let's understand that these coin tosses are going to be independent from one another. And if they are independent from one another, we could actually write it as probability of a head multiplied by probability of a head multiplied by probability of a head. And according to a model, that would be P times P times P equals P cubed. So we can write the probability of this outcome here as P cubed. Now similarly, with the same logic, the probability of getting 2 heads and a tail would be P square Q. Again, 2 heads and a tail would be P square Q. Of getting 1 head would be P, getting 2 tails would be Q square. Again, 2 heads, so P square Q. And here we're going to get 1 head and 2 tails, so PQ square. Here again 1 head and 2 tails, PQ square. And here 3 tails, would be Q cube. So these are the probabilities of getting any one of these outcomes. Okay, so we've written the outcome here and what is the probability right here. Now let's just check that if this is a financial this is a model that we've created. Actually, let's just make sure that our model agrees with our intuition. So let's define an event. Okay, let's define an event A equals getting the first coin toss a head. So we want our first coin toss to be a head. That's the event that we define, and we would actually like to find out what is the probability of getting a head on the first coin toss. Okay. So if we look at all our our sample space, we could see. Let's figure out what are the events, what are the outcomes actually that result in head on the first coin toss. So we see 8 outcomes here. This is the first coin toss, this is the second one, this is the third one. So as we can see, we get a head in these 4 outcomes, okay, only, and whereas the other 4 outcomes would give us a tail on the first coin toss. So we basically, when we say first coin toss a head, we are interested in finding probabilities of getting either a head 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 or a head head tail or a head tail head or a head tail tail. So this is same as a subset containing the following outcomes: head tail head and head tail tail. So this is the subset that we are interested in. We want to find out what are the probability of getting a head on the first coin toss. Now intuitively, we know what is the probability of getting a head on the first coin toss, and that is basically defined right here, equal to find the probability of a head, which is what is the probability that the coin toss results in a head. So that's exactly what our intuition says this should actually lead to. And let's check mathematically if our intuition agrees with our financial model, and that's exactly what we're doing here. So we've listed out all the possible outcomes here that result in a head, and we already have a probabilities listed for these. So this would simplify to probability of a head plus probability of a head tail plus probability of head tail head plus probability of a head tail tail. So this is finding the probability of the subset is exactly equal to, you know, probability of getting all of these, you know, sum of all of these outcomes. So we can write that here as PQ plus P square Q from here plus P square Q plus PQ square. Now further solving this, we could take P square out, so we get P plus Q here. We can take P and Q out, we get P plus Q here again. Now if you see from this equation A, this goes 1, this becomes 1, right? So we are left with P square plus PQ, and we can further solve it by taking P out, and we get P plus Q, and this again is 1, so we finally get P. So as you can see, you know, we started with a model where we defined the probability of getting a head as P, probability of getting a tail as Q. We tossed the coin 3 times. These are the probability of getting individual outcomes. Then we defined an event, and that event resulted in a subset containing 4 elements. We wanted to find out what is the probability of this. Intuitively, that probability was the same as P. Then what we did was we basically solved for this probability. We took a sum of all individual probabilities of all individual outcomes, and after solving it, we also got P. So our financial model kind of agrees with our intuition, which is great. Now what we can do is we can actually generalize this. We could say, okay, we are interested in talking about a probability space. Okay, so we want to talk about a probability space. And that to a finite probability space. Now what is a finite probability space? Finite probability space is basically a probability space we get by conducting an experiment which has finite number of outcomes. So for example, in our coin tossing experiment, we basically had only 8 possible outcomes. So this was basically a finite so a probability space that results from a finite experiment is called a finite probability space. So let's assume that we have a sample space, a finite sample space denoted by omega 1, omega 2, omega 3, da 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 da. So this is basically a generic sample space for us, okay, and we denote an outcome in that sample space as omega 1, omega 2 likewise, okay. So many a time we want to actually talk about a generic element of this sample space, and we actually do not even write the subscripts. We could just write an omega, okay, and omega basically means a generic element of our sample space. So what we want to do is we want to define what a probability space is. A probability space basically needs 2 things. It needs a sample space and it needs a probability measure, okay. Now sample space you already defined, right? It basically is a collection of all possible outcomes of an experiment, okay. So in the previous example, we listed out all possible outcomes of our experiment, and that basically was the sample space. Now we haven't defined what a probability space is. So basically probability space, a probability measure is. So a probability measure is basically a function that maps a generic element of our sample space denoted by omega, and it maps it into a number between 0 and 1. And this is called a probability of that particular outcome. So what is it doing? It basically it's a function that basically takes the outcome and assigns it a value between 0 and 1. Now obviously we need to actually constrain this function a little bit, so we further define the following. We say that if we sum the probabilities of outcomes, okay, of our sample space, and omega ranges the entire sample space, so we're saying that we're taking a sum of probabilities of each and every outcome in our sample space, that should equal to 1, okay. So if we, in other words, if we sum the probabilities of each individual outcomes, that should be equal to 1. Okay. Now, many a time we would also like to calculate what is the probability of a subset of our sample space. Subsets are, we can define it by A, basically any subset of our sample space. Okay, so we want to find out what is the probability of that subset. So if we look at our previous example, we defined an event of getting a head on the first coin toss, and that event basically resulted in a subset defined by these four elements. Okay. Now, when we wanted to find out the probability of those 4 elements, it was same as summing the probability of each of these individual elements. Likewise here. Okay, so same thing here. Now here again we want to sum the probabilities of these outcomes, but instead of the previous example where our omega belonged to the entire sample space, we were summing the probability across the entire sample space. Here we are only going to sum probabilities of those elements that belong in our subset. Okay, so as simple as that. Here we were summing across our sample space. Here we are summing probabilities of only those elements that belong in our subset. That's another important equation. Now, from here, since omega is our sample space basically contains each and every element of our experiment. From here, we can deduce that probability of is very simple, right? I mean, basically, its probability of each element should sum to 1. This basically has each and every element of our experiment, so the probability of getting an outcome in our sample space by definition should be equal to 1. So that's pretty much what I wanted to talk about in probability spaces. So we started with an experiment, and then we just to recap, we basically started with an experiment. We basically defined a financial model here. Then we defined an event of getting a head on the first coin toss, and we made sure that the intuition basically agreed with our model. Then we further went and said, okay, we're going to define a finite probability space, and we said, okay, a finite, if we conduct an experiment that only has finite number of outcomes, that basically is our finite sample space. Okay, and for a probability space, we need a sample space and we need a probability measure. And probability measure is nothing but a function that assigns each and every outcome in our sample space a value between 0 and 1, such that sum of probabilities of all our elements in that sample space equals to 1. And if you want to calculate what is the probability of getting of a subset of our sample space, it's given by this equation. And then we further said that probability of the entire sample space would be equal to 1. So one important thing I would like to actually point out here is, in the last particular lecture when we were talking about random variables, we never really talked about probabilities. So we defined an experiment of tossing a coin, and on that experiment we constructed a few random variables. And as we concluded in the last lecture, that we could construct random variables without really talking about probabilities, right? Now, if you look at this particular example, we've done just the opposite. So here we wanted to talk about probabilities, and we said, okay, we have a finite probability space, and we defined a probability measure on that space. And probability measure, we said, okay, just a function that maps any one of these outcomes into a number between 0 and 1, and that basically is called the probability of that particular outcome. But while we were doing all of this, we never really talked about what the random variable was. So it's important to realize that random variables and probabilities are pretty much two separate concepts. Many a times what's going to happen is, we're going to actually, later down the road, we're going to actually talk about two different measures. We're going to talk about a probability measure in the real world, and we're going to talk about a probability measure in the risk-neutral world. And as we move between the real world and the risk-neutral world, our random variable wouldn't change, okay? A random variable would be exactly what we've defined it to be, only the distribution of the random variable would change. So far we haven't really talked about distribution, and we're going to do that in the next particular lecture, but still it's important to realize that random variables and probability measures are two separate concepts, and when we change the probability measure, the random variable doesn't get affected. Okay, the random variable basically stays the same, only its distribution will change in the two separate measures. So with that, I would actually like to conclude right here. In the next lecture, we're going to talk about probability distributions of a random variable. Either take a 0, it could be a 1, it could be a 2, it could be a 3, and these are the probabilities by which x will take on various values. So probability of getting a 0 for x is 1 by 8, probability of getting a 1 is 3 by 8, probability of getting a 2 is 3 by 8 again, probability of x being 3 equals 1 by 8. So this is called the distribution of this particular random variable x in a probability measure p. Okay, so in this measure, we've defined the probability of heads to be half, probability of a tail to be half. Now, in this measure, in the same measure, we can also calculate the distribution of random variable y. Now, if you see random variable y, it like x, it also takes unique values 0, 1, 2, and 3. So again, we can go and do the same calculation. We can say probability y equals 0. And y would be equal to 0 in this particular subset, in this particular event of getting all 3 heads, and the probability would be 1 by 8. Similarly, we can say y equals 1. That would be given by this particular subset of head, head, tail, head, tail, head, and tail, head, head. This would again be 3 by 8. Probability of getting y equals 2. Likewise would be probability of a head, tail, 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 head, tail, 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 head. Again, that would be 3 by 8. And probability of y equals 3 would be probability of getting tail, tail, tail equals 1 by 8. So if you see, interestingly, the probability distribution of this particular random variable x and y under this measure, which assign the probability of half to head and tail, is basically the same. So the probability distribution under this measure for random variable x and y is exactly the same. So probability of getting a x0 equals 1 by 8, probability of getting a y equals 0 equals 1 by 8. Likewise, probabilities are exactly the same. They are two separate random variables. One is counting the number of heads, the other one is counting the number of tails, and we've defined one probability measure. But incidentally, under this measure, probability distribution for x and y is exactly the same. Now, what we could do is we could change the probability measure. We could say, okay, we have another probability measure. Now, instead of having it 1 by 2, we could say, okay, now we're going to have probability of getting a head, probability of getting a head as 2 by 3, and probability of getting a tail as 1 by 3. Now let's see if in this particular case, what happens to the distribution of the random variables. So how, again, probability of x equals 0 is equal to probability of getting a tail, 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 and that would be equal to 1 by 3 times 1 by 3 times 1 by 3 equals 1 by 27, right? Now probability of x equals 1 would be HTT, probability of getting a HTT, THT, THT, and TTH. Now if we look at this would be probability of getting a head, tail, tail, plus probability of getting a tail, head, tail, plus probability of getting a tail, tail, head. Now if these are independent, this is same as probability of a head times probability of tail times probability of tail. So probability of head is 2 by 3. Probability of a tail is 1 by 3 times 1 by 3 plus what is probability of getting a tail is 1 by 3 times probability of getting a head is 2 by 3 times probability of getting a tail is 1 by 3 plus probability of getting a tail is again 1 by 3 times 1 by 3 times 2 by 3. So you look at this. This is 27, 2. This is 2 by 27 plus 2 by 27 equals 6 by 27, right? Probability of x equals 2. Likewise, we can calculate this, which is same as probability of getting a head, head, tail, head, tail, head, tail, head, head. And again, this would be probability of head, head, tail, plus probability of head, tail, head, plus probability of tail, head, head. And this would be again head probability is 2 by 3 times 2 by 3 times 1 by 3 plus 2 by 3 times 1 by 3 times 2 by 3 plus tail is 1 by 3 times 2 by 3 times 2 by 3. This is 4 by 27 plus 4 by 27 plus 4 by 27 equals 12 by 27. And finally, x equals 3 would be probability of getting a head, head, head equals 2 by 3 times 2 by 3 times 2 by 3 equals 8 by 27. So as we can see from this example, and we discussed in the previous lecture also, random variable and its distribution are two separate concepts, right? So first what we did, we defined a random variable counting the number of heads and tails, and then we assigned some probability measure to it that resulted in some distribution for x and y. And we checked that under this probability measure, the distribution of x and y were exactly the same, right? Then next what we did not change the random variable, we did not change the experiment, so we are still tossing 3 coins. We're still counting the number of heads and number of tails. So our random variable is not changing. But under the new probability measure, the distribution of x has completely changed, right? The random variable hasn't changed, but its distribution has changed. And you can check that the distribution of y has also changed. Okay, you can do the math similarly as I've done for x. And in this new probability measure, the distribution of x and y would not be the same. Okay, so this is a very important concept to understand, that random variable and its distribution are two separate concepts, and this we will use again and again later on when we switch between the real world probability measure and the risk neutral probability measure. Okay, in that case, as I've explained to you earlier, the random variable would not change, but its distribution would change. Okay, thanks guys. So next we're going to talk about some properties of random variables and their distributions. Hi guys, today we're going to talk about expectation of random variables. So let's define our experiment. We're going to take a coin and we're going to toss it twice. The sample space that we get from there is head, 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 tail, tail, head, or a tail, tail, right? Let's also define a probability measure under which probability of getting a head is half and probability of getting a tail is also half. Since these two coin tosses are independent, we could write the probability of a head as probability of a head times probability of a head. That would be half times half equals 1 by 4. You would also notice that since probability of a head and probability of a tail are both half, probability of all of these outcomes would be 1 by 4 as well. So we could write it as probability of head tail equals probability of tail head equals probability of a tail tail. So they are all equal to 1 by 4. So in other words, we could write probability of any outcome omega as 1 by 4 under this measure. Now we would like to calculate the expected value of a random variable. So let's define that random variable. Let's say we have a stock that at time 0 is basically valued at 4. Now if we get a head in any coin toss, then the stock will jump and become twice. Okay, so if we get a head, then the stock will become twice of what it was, so it will become 8. And if it's a tail, it will become half, so it will go down to 2. Okay, similarly, so if we again get a head, the stock will again double up and it will become 16. If it's a tail, it will become half, it will become 4. Likewise here, if we get a head, so which is S1 TH, the value will again become a 4, double of 2. And if we get another tail, it will become half of 2 and it will be 1. So now I would like to calculate what is the expected value of S2. Okay, I want to calculate, so we can get any one of these 4 outcomes, and these 4 outcomes, the values taken by S2 would be 16, 4 and 1, and I would like to calculate what is the expected value of this. So the way we do this is, we need to take the value of the random variable and we need to take a weighted average of that random variable where the weights are the probabilities of those outcomes. So in other words, we need to take the value of the random variable in various outcomes, okay, and we need to weight it by its probability of that particular outcome. So it would be S2 HT, probability of HT, plus S2 tail head, probability of tail head, plus S2 tail tail, probability of a tail tail. So very simple. You basically have taken the value of S2 in various outcomes of the experiment and we're multiplying it by its probability and we're basically adding it up. Okay, so this is basically like a weighted average where the weights are the probabilities. Now doing it mathematically, so we S2 H8 is 16 times probability of each of these events is, or each of these outcomes is 1 by 4, and this would be 4 times 1 by 4 plus 4 times 1 by 4 plus 1 times 1 by 4 equals 25 by 4, right? So expected value of S2 under this probability measure, which assigned a value of half and half to probability of a half and half to a head and tail, basically gives us 25 by 4. Now what we could also do is we could again calculate what is the probability of, the expected value of S2, but in a different measure. So we can define another measure. Under that measure we might say probability of a head is 2 by 3 and probability of getting a tail is 1 by 3. Okay, if that's the case, how would we calculate the expected value here? So expected value under this new measure is denoted by E tilde S2. Okay, and what we need to do is, again, we need to write down the value of S2 in various outcomes and we need to take a weighted average. Okay, so we can write S2 and we're going to say, okay, S2 when there is a head times probability, and which probability? Under the new measure of getting a head plus S2 we can when it's a head tail, and probability of getting a head tail under the new measure plus S2 tail head times probability under the new measure of getting a tail head plus S2 tail tail, probability under the new measure of getting a tail tail, right? One thing to notice here is we've just changed the probability measure, right? We haven't really changed the random variable. As we talked about in the previous lectures, Random variables and probabilities are pretty much separate concepts, right? So when we change the probability measure, we are not disturbing the random variable. Random variable basically stays exactly the same thing, right? The only thing that's going to change is once we change the measure, the probabilities of all of these outcomes will change. And if the probabilities of all of these outcomes will change, then the expected value will change, but the random variable per se under various outcomes will not change. Okay, this will be exactly the same as in the previous probability measure. So that's a very important thing to keep in mind. So likewise, now if you want to calculate probability of a head-head under the new measure, that would be probability of getting ahead, probability of getting ahead. And as we've defined here, in our new measure, probability of getting ahead is 2 by 3. So 2 by 3 times 2 by 3 equals 4 by 9. Likewise, I'm not going to do the entire math here, but you can calculate the probability of getting a head, tail, tail, head, tail, tail, keeping in mind that these coins tosses are independent. So it's simple multiplication of their probabilities. And then we already know what the value of the random variables are, so you can just easily calculate the expected value under this new probability measure. Okay, and you can check that under this probability measure, the expected value of this random variable would be different from the expected value under the previous measure. Now we can generalize this and we can say, okay, we would like to calculate, we have a probability space, and probability space basically means we have a sample space and we have a probability measure, and we have a random variable which is defined on that probability space. Now what we would like to do is we want to calculate expected value of the random variable, right? And how are we going to do with that? So we're going to take what the value of the random variable would be under all the outcomes of this sample space, and we're going to multiply it by the probability of that sample space, and we're going to sum it up. Okay, so it's exactly what we've been doing here. We basically, xw is the value of the random variable for outcome w. Okay, and we're going to sum it across the entire sample space here, right? So coming back, so xw is basically the value of the random variable for outcome w, and pw is the probability of getting that outcome, right? And we need to sum it across the entire sample space, just like the way we've done here, and that's basically is our expectation. Now if we were to calculate expectation under the risk neutral measure denoted by tilde, then it's going to be the same thing, but here random variable, again, as I pointed out, will not change. What would change is the probabilities of these things denoted by p tilde w or omega, and this basically would be the equation, right? Same equation, just the here we're going to have a probability under the new measure, and so expectation under the new measure is basically denoted by this particular equation. Okay, now expectations are linear. So for example, if you have a of x plus b of y, where x and y are both random variables, a and b are constants, this would be expected value of x plus b times expected value of y. In particular, if you have a linear function like a plus bx, and we want to calculate expected value of function of that random variable, this will be equals to calculating expected value of a plus b capital X is a plus b x. This is same as function of the expected value, right? So this basically means that L of expected value of the function of a random variable, linear function, is equal to, okay, this is a very important thing to remember. And if the function wasn't a linear function, it was a convex function. So this was a convex function, and if you wanted to calculate expected value of convex function of x, this would be greater than equal to function of e of x. Now this I'm not going to prove. It's the proof is available in Steve Shreve's book, and this is called Jensen's inequality. Okay, Now let's consider a convex function of x as x square. So if you want to calculate now, if you want to apply Jensen's equality to this, it would be e of, now we're going to substitute by capital X, e of x square is greater than equal to e of x whole square. This basically comes right from Jensen's inequality, and keeping in mind the convex function of x square. Okay. So guys, so that's all I wanted to talk about today. In the next lecture, we're going to talk about conditional expectations. See you then. Bye. Hi guys. So today let's talk about conditional expectation. So let's repeat the experiment from the last class. So we're going to take a coin and we're going to toss it 3 times. Okay. Let's also have a stock whose value at time 0 denoted by S0 is 4. And every time we toss a head, the stock would double up. And every time we toss a tail, the stock would go down by half. Okay. So let's see what happened in the first coin toss. We can either get a head or we could get a tail, right? And as we said, if we get a head, the stock would double up. So it will become 8. If we get a tail, the stock would become half. So it would become 2. So now we can do another coin toss. And now in the second coin toss, we can have these possible outcomes. We can have either 2 heads, okay, or we could have gotten a head and then a tail, or we could have gotten a tail and then a head, or we could have gotten 2 tails. These are the only 4 possible outcomes when we toss a coin 2 times, right? So again, repeating the same thing, every time we get a head, we're going to double the stock up, so it will become 16 here. If we get a tail, it will become head tail, it will become 4, right? Because it becomes half. Again, if from tail we get a head, so it becomes S2 tail head, the stock would go from 2 to 4, so that would be 4. And if we get another tail, it would become half of what it was, so it would become 1. Now we can, extend this experiment for another coin toss, and let me just do that very quickly here. So we can get another head, head. That would become 32. We could get a tail, head, tail. That would be the same as S3, head, tail, getting a head here. S3, tail, head. And that would basically make it 8. Or we could get S3, head, tail. S3, tail, head, tail equals S3. Tail, head equals to 2, or we could get a tail, that would be 0.5. So what I've done is I've basically written down all the possible outcomes here, okay, and the value of the stock in all these possible outcomes is also listed right here, okay. So this is basically how we're going to define a process, okay. So now let's basically take it a step further. Let's also define a probability measure under which probability of getting a head is half and probability of getting a tail is also half. Okay. And let's also define a time, concept of time now. Let's say this is time equals 0, or time equals 1. This is time equals 2. And this is time equals 3, and this is time equals 0. Okay, so what we're saying is that time 1 we have already tossed the first coin, okay, and we know what is the outcome. Either it's going to be a head or a tail. By time 2 we've tossed the coin twice and we know what is the outcome of the first 2 coin tosses. Okay, it's going to be either head, tail, head, or tail, but we know exactly which one of these outcomes have we arrived at. Okay, at time 3 we know all the 3 outcomes. We know either if we toss the head or head tail, or you know, all of these, any one of these possible outcomes, right? So you can think about, you know, time as we move forward in time, we get more and more information about the coin toss, right? So when we are standing at time 0, we haven't yet tossed any coin, and we really don't know how the coin tosses would behave, right? At time 1, we know the first coin toss outcome. At time 2, we know the 2 coin toss outcomes. And at time 3, we know the outcome of 3 coin tosses. So as we move forward, we get more information. Okay? So think of time moving forward as we getting more information in our experiment here. Okay? And the information that we're looking at is basically what were the outcomes of our coin tosses. Now let's say we know that S3 is a random variable, right? And right now at time 0, we don't really know what the value of S3 is going to be, right? It can be any one of these possible values depending on how the 3 coin tosses behave. Now, let's say we want to estimate the value of S3, okay, at time 2. So please note that, you know, S3 is a random variable whose value depends on the 3 coin tosses. Okay, at time t2, we only know the outcome of the first 2 coin tosses, right? We don't know how the 3rd coin toss will behave. So we need to estimate the value of S3 at time S2, and that basically is called conditional expectation. And what is it conditioned on? It's based on we're going to take the expectation of S3 condition on the information available to us at time 2. And as we just discussed, the information available to us at time 2 is, you know, the results of the first 2 coin tosses, right? So in particular, what we want to do is we want to find out the expected value of S3 at time 2. And the way we denote that is we write a E and a subscript 2. That basically denotes that you want to calculate the value of the expected value of S3 at time 2. Okay, but expected value of S3 at time 2 we can calculate under these 4 possible outcomes, right? So we can, you know, we can calculate the expected value when we got the first 2 coin tosses were head. We could calculate the expected value of S3 at time 2 if the first 2 coin tosses were either head tail, and we can calculate expected value of S3 at time 2 if it was a head tail head, or we could get expected value of S3 if it was a tail tail. Okay, so these were the 4 possible outcomes when we toss the coin 2 times, and we need to actually get the expected value of S3 at all of these 4 points. Okay, so that's how we've denoted this. Now let's take the example here that we want to calculate expected value of S3 when we got the first 2 coin tosses as a head. Okay, if you're standing right here, then we know that in the next coin toss, okay, we would either be at 32 or we would be at 8. So if we got a head from here, the stock would jump up to 32 or it would go down to 8. So there were only 2 possible outcomes, each with the probability of half, right? So if we are standing here at head and we wanted to get the expected value of S3, it would be the value of S3, which is 32, times what is the probability of getting a S3? I mean, of getting a 32. It's half, right? Because we already know what the first 2 outcomes were, so we were already here. Now we would toss a coin again. Either we would get a head or a tail, and if we got a head, we would be at 32. If we got a tail, we would be at 8, and the probability of getting a head or a tail are both half, right? So if you want to get an expected value of this, it would be 32 times half plus 8 times half. That would be 16 plus 4 equals 20, right? It's very simple. Only 2 possible outcomes in the next coin toss. We are already standing here, so we just need to figure out what the value of the random variable is and multiply it by the probabilities. and the probability in this case is going to be just half of getting a head or a tail. Likewise, we can quickly calculate expected value of S3 if we got the first two coin tosses a head tail, so that we are here. Now in this case we are already at 4. If we get a head in the next coin toss, we will be at 8. If we get a tail, we would be at 2. So expected value would be 8 times half plus 2 times half equals 4 plus 1 equals 5, right? And this would also be same as expected value of S3 if the first two coin tosses resulted in a tail head. Because if it was a tail head, we would be exactly at the same point, and in the next coin toss we could either get a head 8 or a 2 with the probability of half. So this would be same as this, okay? Now the final thing we need to calculate is we can calculate expected value of S3 if the first two coin tosses were tail. Okay, we were here. Then we could get either a 2 with a probability of half, or we could get a half with a probability of a half. So it would be 1 plus 0.25, 1.25, right? So what we've done so far is basically we've calculated the expected value of S3 at time 2, okay? And at time 2 we knew that we could be in either one of these 4 states, okay? And we need to calculate the expected value of S3 in all of these 4 states, okay? Now keep it in mind that this expected value, okay, E2 of S3, I'm not going to write the coin tosses here in bracket, okay? E2 of S3 is also random, okay? So because this expected value depends on the first two coin tosses, right? If the first two coin tosses were head-head, then this quantity would be equal to 20. If it was a head-tail or a tail-head, then this particular expectation would be a 5. And if we got a tail-tail on the first two coin tosses, then the expected value of S3 would be 1.25. And at time 0, we don't know if we're going to get a head-head, a head-tail, or a tail-head, or a tail-tail in the first two coin tosses. So that means that this particular expectation is random at time 0, right? Because we really don't know, and you know, how the first two coin tosses are going to behave, and depending on the two coin tosses, the expected value will change, okay? So very important thing to keep in mind, that the expected value of S3 at time 2 would be random. So like we've calculated the expected value of S3 at time 2, we can also calculate the expected value of S3 at time 1, right? So let's do that next. So I've written down the same stock process here. So what we want to do now is, this is time 1, and we want to calculate the expected value of S3 at time 1. So keep in mind, at time 1, we can have either one of these two outcomes, head or a tail. So we want to calculate the expected value for each of these, okay? So we can denote that as, we want to calculate the expected value at time 1 of a random variable S3 if the outcome was a head, or we can do the same thing, expected value at time 1 of random variable S3 if the first outcome was a tail. And how are we going to do that? Same as what we've done here. We're going to look at all the possible outcomes of S3 that we can get from this point. So if we have already tossed the coin once, we are here. Now there are 2 more coin tosses remaining. And in those 2 coin tosses, we can get either a head-head, head-tail, tail-head, or a tail-tail. So let's write that. So if we get 2 more heads now, what would happen to the stock price? It would go to 32. So 32 times probability of a head-head plus, in the next 2 coin tosses, we can get a head-tail also. If we get a head-tail, the stock would go to 16, then come down to 8. Probability of getting a head-tail, or we could get a tail-head that would result in stock price as 8. Probability of a tail-head, plus we could get from here 2 tails, and we would be down to 2, and probability of getting a tail-tail. And all these 4 probabilities are equal to 1 by 4. So this would be equal to 32 times 1 by 4 plus 1 by 4 plus 8 times 1 by 4 plus 2 times 1 by 4 equals 12. So this is 8 plus 2, 10 to 0.2, 12.5, right? Okay. Likewise, if you want to calculate the expected value of S3, if you were at this particular outcome, then that would again be from here we can get 2 heads, but if we get 2 heads from here, the stock would become 8, right? And probability of getting 2 heads from here, plus if we can get likewise here, we can get a head tail, but the stock would go up to 4 then come down to 2, probability of getting a head tail, plus again probability we can get a tail head, so that would be probability of a tail head, plus we could get 2 tails like here, but then the stock price would go down to 0.5, probability of 2 tails. Again, this would be 8 times 1 by 4 plus 2 times 1 by 4 plus 2 times 1 by 4 plus times 1 by 4. This would be 3.125. Okay? So quite simple, right? So what we've done is, again, we basically have calculated the expected value of S3 at time 1, and it's denoted by E1 S3, either we get a head or a tail. Okay, now also to note is, again, E1 of S3 is actually a random variable, Why? Because, you know, if we get a head or a tail, the value of this expectation would change, and at time 0 we don't really know if the first coin is toss is going to be either a head or a tail, right? So if we get a head, the expected value would be 12.5. If we get a tail, expected value would be 3.125, and it's random because we don't know how the first coin toss is going to behave, right? Now, one thing more to note is, if you want to take expected value of S3 without any information, which would be expected value of S3 without any information, means expected value at time 0. This is the same thing as expected value of S3. Okay, calculating the expectation without any information is simply we can drop this subscript and denote this by E of S3. And this expectation we've already calculated. We've learned to calculate in the previous class, right? How do we calculate expected value of any random variable? Let's say a random variable is X. Expected value of the random variable is, we sum the value of X across various omegas, multiplied by its probability, and omega goes in, ranges within the sample space, right? So likewise, if you want to now calculate expected value of S3, we could write similarly as omega belongs to capital Omega, S3 of omega times probability of omega, where omega would be any one of these values, right? Okay, that's how we calculate S3, expected value of S3. But one thing to note is, expected value of S3 without any information doesn't depend on any of the coin tosses. Okay, so expected value of S3 without any information, as you can see, is it basically doesn't depend on a coin toss, and so this quantity is not random. It's very important to realize this, not random variable. So when we calculated expected value of S3 at time 2 and expected value of S3 at time 1, both we said dependent on the coin tosses, okay, and they were random. But expected value of S3 at time 0, which we calculate like this, is not a random variable because it doesn't depend on any coin toss. And this is an extremely important concept, okay, to realize. Now, that's pretty much all I wanted to discuss for conditional expectations, okay. In the next class, we're going to start talking about properties of conditional expectations. 3 plus 1.5 equals 22.5. Okay, so here you can see the right hand side was 22.5, the left hand side is also 22.5, so this first equation is basically satisfied. Now we can similarly do it for equation number 2, make sure that the right hand side is equal to the left hand side. I'm not going to do that, I'm going to leave it to you guys to basically give it a try. Okay, and you'll see that obviously the left hand side and the right hand side would be equal, hence this equation holds, and we basically have just checked the linearity of conditional expectations. Now what we can do is, we can also apply the same concepts to taking out what's known, iterated conditioning and independence, and we can make sure that we understand how this mathematics works. I'm not going to do that here, but if you guys are interested, Steve Shreve's volume 1 has given example of applying all of those properties to this particular model. You can check it out there, but what I suggest is you basically try to do it yourself. Okay, you try to do it yourself, you'll actually learn more, you'll understand this concept a lot better. So that's pretty much all I wanted to discuss here about conditional expectation and its properties. In the next class we're going to talk about martingales. Okay, so I'll see you then. Bye. Hi guys. So today let's talk about martingales. And martingales are extremely important in finance because they are the foundations for no arbitrage theory and risk neutral pricing. Okay. So in this class what I want to do is I want to describe what a martingale is, and later we're going to use this martingale property when we're doing risk neutral valuation. So let's start with the adaptive stochastic process. And by adaptive stochastic process, I mean we have a sequence of random variables m0, m1, m2, mn, where each one of the random variables mn depends only on the first n coin tosses. Okay, this is called the adaptive stochastic process. Now we say adaptive stochastic process is a martingale if we take expectation at any time n of a random variable mn plus 1, then this is equal to m of n for all n from 0 to n minus 1. Okay, so as you can see, this basically is a one step ahead property. So we basically are taking expectation at time n of a random variable m of n plus 1. Okay, now we can also make it a two-step property. So m of n plus 1 we can write as expected value of n plus 1 m of n plus 2, right? And this comes from our martingale property, right? So if you can write it like this, and you can see we can take iterated conditioning here, and that would make it m of n plus 2 equals mn. Now this has become a two-step ahead property, right? Now the random variable is 2 steps forward. Now likewise we can actually do it for mn plus 3 likewise, and we can make a generic expectation. What we could say is expectation at time n of a random variable m is equal to, so this is called a multi-step ahead martingale property. Okay, so it follows from here that m0 is equal to expectation at time 0, so I don't have to write a subscript here, of m1. Okay, and from a multi-step ahead property I can also write expectation of m2, expectation of m3, expectation of mn. So as we can see from here, for a martingale process the expectation remains constant. Okay, as we go forward, so the expectation doesn't change. Now what I would like to do is, let's actually apply this property to our simple model, okay? We basically had defined a stock process where at time 0 the stock was at 4. If we tossed the head, then the stock went up to 8. If we tossed the tail, then the stock went down to 2, okay? Now let's define a probability measure under which probability of getting a head is 1 by 3 and probability of getting a tail is 2 by 3. Let's calculate, what I would like to calculate, the expected value at time 0 of random variable S1, okay? And what would that be? At time 1, random variable can be either 8 or 2, right? With probability 1 by 3 and 2 by 3. So expectation is 8 times 1 by 3 plus 2 times 2 by 3 equals 12 by 3 equals 4, right? And 4 is the same as where we started. So this can be written as S0. So from here we can see the expected value of random variable S1 at time 0 is equal to S0. And this pretty much is the same thing as how we define a martingale, right? So we said for a martingale, expected value at time n of mn plus 1 equals to mn. So likewise here. Okay, so this basically becomes the martingale under this probability measure. But if we had defined the probabilities to be probability of a head to be half and probability of a tail also to be half, then the expected value would have become 8 times 1 by 2 plus 2 times 1 by 2 equals 5, right? Then the expectation would not have been equal to S0. So in this case, in this probability measure, we can see S0 is less than expectation at time 1. And such processes are called sub-martingale. Okay? So martingale, the expectation is 0. Sub-martingale basically have a tendency to rise. So we can see expectation of S1 at time 0 is higher than S0. So they tend to rise, okay? If on the other hand, in another probability measure, if it was like this, if the expectation had a tendency to go down, then this would be called a super martingale. Okay? Sub-martingale, super martingale. Sub-martingale have a tendency to rise. Super martingale have a tendency to fall. But martingale, basically the expectation remains constant. Okay? The expectation doesn't change. And this is actually extremely important. Martingales are extremely important in mathematical finance, as we will see later. So at this point in time, that basically what I wanted to talk about in this particular lecture. So we've defined what a martingale is, and I showed you, under this measure our stock process was a martingale, and this measure our stock process was a sub-martingale. Okay. So in the next lecture now, we're going to try to come up with our risk neutral pricing formula for a binomial asset pricing model. Okay, and there you will again see martingales, and hopefully the concept is going to get clearer. Okay, all right guys, thanks. Double up. So if you get a head, the stock will double up and it goes to 8. And if you get a tail, the stock will become half and become 2. Let's also now assume that we have a money market account that pays us an interest rate R, and for this particular example, let's consider R to be 25%. So what that means is if we put in $1 in the money market accounts today, at time 1, it'll grow to $1.25. Okay, very simple. Now what I would like to do is I would like to calculate the value of a European call option. Okay, and most of you already know what a call option is. A call option is basically a security that has a payoff equal to max of S1 minus K and 0, where K is the strike price. Okay, so let's assume for our European call option K is equal to 5. Okay, the strike price is 5. So in this particular situation, when the stock goes up, what would be the value of a European call option? Let's denote that by V1 of H. That will be 8 minus 5, max of 3 and 0. That would be just 3. Okay, and likewise V1 of tail would be max of 2 minus 5, which is minus 3 and 0. So max of minus 3 and 0 is 0. So this is the payoff of a European call option. If we either get a head or a tail, you know, and the stock would be at 8 or 2. Okay, so quite simple. And what we want to do now is, we know the value of the European call option at time 1. It would be either 3 or 0. We want to calculate what the value of this European call option at time 0 would be. Okay, so that basically is our goal, to calculate the value of this call option. Now, many years back, I remember the first time when I saw this problem, I thought the approach should be that, you know, we know what the value of the call option here in these two states is. So if I can figure out what is the probability of coming to this state, then it could be simply, the value would be simply V0 equals, let's say the probability of going up is P, then I will say V1H plus Q, which is probability of going down, times V1T, and that's the value of the option I'll get at time 1, and I need to discount it, so I can do 1 plus R. Okay, so that's what I thought initially when I first saw this problem, that we could actually take this approach and calculate the value of the option. But the problem is, with this approach is, we don't really know what P and Q is going to be. What is the probability of going up, probability of going down? It's not really easily, you know, we can't easily go out and calculate. If you ask 10 different people what the probability is going to be, they're going to give you 10 different answers. And if you use different estimation techniques, then, you know, if you ask 10 guys to basically estimate what the probability of going up and down is, they will come up with different answers. So if you take this approach, we will not get too far. Okay, because probability of up and down is, you know, it's not very clear which probability we should be using. But turns out that there is another approach to calculating the value of this option at time 0, and it's a very powerful technique, and it's called the no arbitrage pricing. Okay, so what we're gonna do is, instead of using this approach, we're gonna say, okay, this let's not do. Let's somehow use the money market account and the stock itself to figure out what the value of this option is. And the way we're going to do it is, let's assume that at time 0, we buy delta 0 stock. Okay, we buy delta 0 stock. Now, buy delta 0, buy stock. And let's also assume that we basically, B0 is some quantity of money that we put in our money market account. Okay, so we have two positions at time 0. We basically buy some stock, delta naught stock, and we put some money, B0, in money market account. Okay, I would like to figure out what is the value of this portfolio at time 1. So since we have at time 1, we could have either tossed a head or a tail, and we could be either in this state or this state. We could have the value of a portfolio, which I'm going to denote by X1. So value of the portfolio at time 1, if we get a head, could either be delta 0, which is the number of stocks that I had, times the value of that stock now would be 8, plus B0 was the money that I put in my money market account, and it would grow by a factor of 25%, which is 1.25. Okay, and likewise, if I want to figure out what is my value if I toss a tail, that would simply be the number of stocks that I had times the value of the stock, which is 2 in this case, and the same equation now, which is 1.25. This is my money market account, this is my stock position. Now what I would like to do is, my argument of no arbitrage is that I would like these, the value of my portfolio to be equal to the value of the option. So when I get ahead, I want this value of my portfolio to be equal to value of the option, which is 3. And likewise, if I toss a tail, then I want this value of the portfolio to be equal to value of the option again, which is 0. Okay, so what I've done is I had 2 different states for my portfolio, and in these 2 different states I've equated the value of the portfolio to the value of the option. Okay, so now we have 2 unknowns, delta naught and B naught, and we can solve for them. We have 2 equations, 2 unknowns, we can solve for them. So what we can do is we can subtract these 2 equations, and if we subtract these 2, we'll get 6 times delta naught equals 3. That basically makes delta naught equals half. Okay, and if we do now, if we substitute delta naught equals half in the first equation, we will get 4 plus B naught 1.25 equals 3. B naught equals minus 1 by 1.25 equals minus 0.8. Okay, so we had 2 equations with 2 unknowns. We solved for them, and we got delta naught as half, and we got B naught as minus 0.8. Okay, now, so if delta naught is half and B naught is minus 0.8, then we know that the value of our portfolio will be the value of the option. Okay, so we have now simultaneously created a portfolio of stocks and bond, or stock and money market account, okay, that equals the value of our option in all future possible states. So in future we could have had a head or a tail, and we could have had a value of 3 or 0 for our option, and we created a portfolio which replicates this option. Okay, now what arbitrage pricing theory says that if you have 2 securities that have the same price or same payoffs in all possible future outcomes, then the value of the 2 securities should agree at time 0. So that means the value of the 2 securities should be the same at time 0 also. So in this case, we've been able to replicate this option by using this portfolio. So value of this portfolio at time 0 should be the value of our option. So what it's saying is, now the value of our option at time 0 should be the value of this portfolio at time 0. So what was the value of this portfolio? We bought delta naught stock. Delta naught was half, so half. And what was the value of the stock at time 0? That was 4. And we had B0 money in a money market account. B0 was minus 0.8. So this is basically 2 minus 0.8 equals 1.2. So this is our value of the option according to no arbitrage pricing model. Okay. So let's recap this theory. So we had a stock where it could take 2 possible states in the future, and under these 2 possible states, the value of a European call was given by V1 of H, and that was equal to 3, and option could be either at 0 also. Then what we did was we said, okay, we're going to create a portfolio of stock and money market account that will replicate the value of this option at time 1. So we came up with 2 different equations, and we had 2 unknowns. We solved for them, and we got the value of delta naught as half and B naught as 0.8. Then we said, okay, according to no arbitrage pricing theory, if there is a portfolio that replicates the option, then the value of that portfolio at time 0 should be the value of the option. So we just calculated we substituted these values, and we got the value of the option as 1.2. So what our model now says is, in order to prevent any arbitrage, the value of the option should be 1.2. Now, what I would like to show you next is that if the value of the option is different from 1.2, then how will there be an arbitrage and how we can take advantage of it. Okay. Hi guys, so I just showed you that if you have the previous option The fair value of the option is $1.2, right? Now let me show you what's going to happen if the option is trading at, let's say, $1.21 in the market. How we can take advantage of this situation. Okay, so let's say we are at time 0. Okay, because the option is trading higher than what our model suggests. Okay, let's sell this option in the market. So sell option in the market at time 0. How much money we will get if we sell the option in the market? We'll get $1.21 today. It's a positive number because it's a positive cash flow. We're getting $1.21 to us. Okay. Now what we're going to do is, since we have sold this option, we need to replicate this option. Okay. So what we can do is, if you remember in this, here I showed you that we can replicate the same option at a cost of 1.2. And what did we do to replicate the option? We bought half a stock and we borrowed $0.8 from the market. So what we can do is buy half stock, and since the value of the stock at time 0 is 4, how much money do we need to shell out to buy half a stock? That will be minus half into 4 equal minus $2. And why minus 2? Because it's a cash outflow. Okay, so this was the cash inflow, this is the cash outflow, and we borrow $0.8 from the money market account. So this is a positive cash flow. Okay, so if you look at our cash flow now, we get $2.01 and we pay $2. So net cash flow is positive $0.01. Okay, very simple. Now let's see what's going to happen to this portfolio, all the things that we've done at time 0. What do we have to do at time 1? See, because we have sold this option, okay, now at time 1, we could have either tossed a head or a tail, and the value of the option would have been either a 3 or a 0. Okay, now since we've sold this option, the person who's bought this option would expect $3 from us if there was a head, or it would expect nothing from us if it was a tail. Okay, so we don't know if it's a head or a tail right now. So at time 1, the sell option position would either require us to pay 3 or 0, right? If it was a head or a tail. Okay, now half a stock. Now because we bought half a stock, what would be the value of the stock at time 1? Well, at time 1, the value of the stock would be half times 8. If we get a head, that would be 4. Okay, or the value of the half the stock would be 1 here. And what we can do at time, so this is my option position. Okay, so I owe $3 here and 0 here. Half a stock is worth 4 or 1. And what I can do is, whatever be the outcome, I'll just sell the stock at that time. Okay, so this would be my positive cash flow. So my stock position is worth 4 or 1 if I get a head or a tail, and I'll just sell it. So it will be positive numbers here only. Okay, positive. And since I had borrowed 0.8 today, I will basically owe the bank, okay, 0.8 times 1.25, right? And that would be $1. So I basically owe the bank, and I'll have to pay, so it'll be a -1 in both the situations. Okay, so what I can now do is I can look at what my cash flow is going to be if I get a head. So if I get a head, then I owe $3 in the option, but I get 4 from my stock, and I need to pay 1 to the bank. So if I sum all of these, I get a 0 here. Okay, likewise, if I sum all of these numbers, I get a 0 again here. Okay, so you can see what's happening at time 0. I basically had a net positive cash flow of 1 cent, but at a future time I had no liability. If I toss the head or a tail using this strategy, I will not make a loss. Okay, so this is exactly what arbitrage is. So we basically making money out of nothing. We have 0 probability of losing this money and some probability that we actually make some positive money. So we basically have made some money at time 0 by using this strategy. But in the future, there was absolutely no chance of losing any money, right? And this is exactly what arbitrage is, okay? And in actual markets, arbitrage opportunity might happen sometimes, but the moment people see an arbitrage opportunity, so for example, if option was really trading at 1.21, in order to take advantage of the arbitrage, people will start selling this option, okay? And if you sell this option, the value of the option drives down. So it will keep driving down till it reaches $1.2, and that will be the equilibrium state, because this is where the arbitrage vanishes, okay? So I showed you how we can take advantage of the option if the option is trading higher than the market. Higher than what our model suggests, right? We can do this and we can take advantage of the situation, and we can see the cash flows of this strategy at time 0 and time 1, and we see there is no way we can lose money, and we only end up making money using this strategy. Hence, there is arbitrage. Likewise, you can do the same exercise. Let's say if the option is being traded at 1.19, which is lower than 1.2. In that case, option is available cheaper than the market, and what we can do is at time 0, instead of selling the option, we can buy this option. If we buy option, we have to shell out this money, so the cash flow will be negative. Instead of buying this stock, we will sell the stock. We'll do whatever we have done here, we'll just do the opposite. So selling the option, we'll buy the option. Instead of buying half the stock, we'll sell half stock. If we sell half stock, this cash flow will become positive. So instead of paying $2, we'll get $2 today. And instead of borrow, we are lend 0.8. So instead of getting a positive 0.8, we get a minus 0.8. Okay. So if you see, this is 2 and this will be 1.99. So this will give us a positive cash flow again of $0.01. Okay. And time 1, if we buy an option, we will either be at positive 3 or 0, because we sold this stock. This is head or tail. So at time 1, because we bought this option, if we get a head, it will be worth 3. If we get a tail, it will be worth 0. Because we sold half a stock, we have short sold half the stock, we need to now cover it. And at time 1, we need to either pay $4 to cover, or we need to pay $1 to cover, because half the stock, just, it will be just negative of this. And when we lend money, we will get $1 back from the bank. So this is positive 1, positive 1. So if you add them up, you will see if we get a head, all the cash flows will cancel out, and we get a 0 cash flow here. Likewise, we get a 0 cash flow here. So using this strategy again, we've taken advantage of the situation. At time 0, we got a positive cash flow. At time 1, there was no chance of us losing any money because of this strategy. And again, we made an arbitrage profit of $0.01. Okay. And what would happen is, as this arbitrage opportunity gets exploited, more and more people buy this option, and that will drive up the price because there is more demand for this option. And as the price gets closer to 1.2, the arbitrage opportunity would evaporate, and that would be the fair value of the option. Okay, and it will start trading at 1.2. So great. So I showed you, how we can take advantage of arbitrage opportunity if either this option is trading higher than what our model suggests or lower than what our model suggests. In both the cases, I showed you what strategy we can use to take advantage of this arbitrage opportunity. So according to arbitrage theory, the value of the option should be 1.2, and the moment it deviates from that, market participants will do what we've done here and take advantage of the situation. And as more and more people do it, it will basically make the market price of the option equal to our no arbitrage price. Okay, so it's a very powerful theory, no arbitrage theory. One thing to keep in mind here is, as we were calculating the value of this option, here we said we need the probability of stock going up and down, but according to the arbitrage theory, we never really needed any probabilities. Okay, if you saw, we did all these calculations without really requiring what is the probability of going up and down. Okay, and that is the main advantage of using arbitrage theory, is that the probabilities of stock going up or down doesn't really matter. What really matters is by how much the stock can go up or down. So these values matter, but not the probabilities of stock going up and down. It's a very powerful theory, and we're going to actually expand on this theory in the